welcome back, class. In this video, we are going through Chapter 2, Section 3, Graphs that Enlighten and Graphs that Deceive. So in Section 2.1, to recap, we did frequency distributions, which talk about the classes and then the frequencies that each class has, the occurrences. Then we took those tables and then in section 2.2, we plotted them on a histogram, which is basically a bar graph. We are now going to continue with different ways to display data on various graphs and charts that are really going to help us visualize things a little bit easier than just looking at a table of numbers. So another common graph that we'll be using is a dot plot. A dot plot is a graph of quantitative data in which each data value is plotted as a point or a dot above a horizontal scale. So dots representing equal values are stacked. So the features of a dot plot is it displays the shape of a distribution of data, and it is usually possible to recreate the original list of data values. Now what we mean by that is on a histogram, one of the flaws of a histogram is when you're looking at a histogram, you can't actually recreate the original list of data values because you have the data listed in classes. So in our last example, say we had a class that had a lower limit of 75 and an upper one of 85, and then there were 8 occurrences. Well, I don't know if that meant that 8 of them were 75, 8 of them were 76, a common mix of the both. You can only know how many were in each class, but not of each individual value. A dot plot, these are a little bit easier to tell. Now this one actually isn't the best example. Usually they have them numbered a little bit easier, but you'd be able to say this is 40, this is 41, the 2 are exactly 50, this one might be like 51, 52. Usually they're actually a little bit more labeled than this, but you get the idea that there were intermediate like tick marks right here. You'd be able to tell if each tick mark was 2, then this would be 42, this would be 52, this would be 92, and so on and so forth. You can tell this is generally a normal curve-ish, but that's a dot plot for you. Similar to a histogram, but different benefits as well. Then we do stem plots or stem and leaf plots, and these represent quantitative data by spreading each value into 2 parts. The stem, which is the leftmost digit, and the leaf, which is the rightmost digit or digits. So here is 4, slash line 0, 2. So this represents that pulse rates of, remember, the stem is this right here, and then the leaf is this whole part right here. So this would say that there are 2 data values in the 40s, 40 and 42. This would tell me of all the 50s, things in the 50s, 50, 50, 52, 52, 52, 52, 52, 54, 54, and so on. This would be 90, 92, 94, 96, 96, 102, and 104. So over here is your stem, which is your leftmost digits, and then the leaf is the final digit. So this kind of features is it shows the shape of the distribution of the data. Again, you can tell that this is sideways now, but again, kind of following that normal bell-shaped curve-ish. It retains the original data values, and it automatically sorts the data samples. So 40 would be the minimum, and 104 would be the maximum. So that would be a stem plot. The next type of graph is the time series graph. And a time series graph is a type of data in which quantitative data has been collected at different points, such as monthly or yearly, and then you pretty much just connect the dots. So in 1985, you had 175 law enforcement fatalities. In 1990, you had 160, and all those in between. And then you just pretty much connect them and then see where basic trends are moving. So this reveals trends over time. Are you increasing, decreasing, up and down, uniform, etc., etc.? Next is a bar graph. You all should know how to deal with the bar graph. Graph of bars of equal width, that's important, to show frequencies of categories or categorical data. and these bars may or may not have gaps between them. So you can also use bar graphs for non-quantitative values. You can do them for categorical data as well. Pareto charts is like a bar graph, but the only additional factor is that the bars are to be arranged in descending order. So the bars decrease in height from the left to the right. So similar to a histogram, they show relative distribution of categorical data, and it draws attention to more important categories. So again, this is categorical data. So you're looking at non-quantitative things along the x-axis, and you start with the most on the left, and then you go in decreasing order of heights as you move from left to right. Pie charts, again, another one you should be very familiar with. They depict categorical data as slices of a circle in which each slice is proportional to the frequency count. So this is the same data as shown in this Pareto chart, just in a pie chart form, showing that jet skis is the majority of it, and then going down in descending order. Each one would have respectively less pieces of the pie. Frequency polygon, a graph using line segments connected to points located directly across midpoints. So this is similar to a histogram, but it uses line segments instead of bars. So instead of having them being bars right here, now we're looking, these points right here are the midpoints of all the classes, and then you're just playing connect the dots again. So same maximum values, but now we're looking at the midpoints to analyze the x-axis right here. Relative frequency polygon, if you put them side by side with the McDonald's and the Dunkin' Donuts for drive-through lunch times, you can see how, in general, the Dunkin' Donuts has much fewer times per drive-through session. So those are all the graphs that enlighten. Now we will talk about graphs that deceive. And the idea of a graph that deceives is, although they're not lying to you in the way they portray the graph, they are intentionally missing a piece of information or just portraying the graph in a way that'll make you draw a conclusion that isn't true. So a common deceptive graph involves using a vertical scale that starts at some value greater than 0 to exaggerate differences. So right here, if you just look at the left, oh crap, like OxyContin is much, much, much more powerful than the placebo. Oh, but look, this starts at 10% and this is only 22%. So the graph makes it look like this is, what, 10% more powerful. But now if we look at them starting from 0%, well, it's still dramatic, but not as dramatic when you start from 0 compared to starting at a non-zero point. And that concludes this section. Thank you.